Welcome to another Essential Explainer. I am your host, and today we are stepping directly into the mind of the Cambridge examiner. We are going to decode one of the absolute most notoriously tricky, misunderstood, and frankly grade-dropping areas of the entire Cambridge AS and A-level computer science syllabus. Specifically, we're zeroing in on the 9618 course, and we are going to master special purpose registers. But we aren't stopping there. We are zooming right in on the big one, the index register, or IX. Now, a lot of you watching probably built your foundation in earlier syllabus codes. Maybe you took 0417 or 0478, maybe you came up through 0983, 0984, or even 2210. Those gave you the building blocks. They taught you what a register is, but 9618 is a completely different beast. You can't just define things anymore. You have to analyze them. To really set the stage for this challenge, I want you to visualize a dynamic split screen right in front of you. Picture a clock ticking down. The tension is high. On one side of the screen, we have an actual Cambridge past paper question. Let's say it's a really rigorous data extraction problem requiring indexed addressing. On the other side, we have two typical students taking this exam. Let's call them Alex and Sam. Alex is what we call the knowledge overloader. Alex looks at this question and just starts sweating facts. Alex writes down every single raw computer science fact about registers, memory addresses, binary sequences, logic gates, you name it. The page is full of ink, but there is zero actual analysis. It's just a textbook dump. On the other side of our split screen is Sam. Sam is the rusher. Sam completely ignores the command words in the prompt. Sam misses the explicit requirement to show working, skips all the logical steps, and just jumps straight to a final numerical answer. If we were to hand these papers to a senior Cambridge examiner right now and hold a red pen to them, it would be an absolute bloodbath of lost marks. Both Alex and Sam are leaving easy points on the table. This explainer is your ultimate strategy guide to ensure your exam paper is covered in green check marks instead of red ink. We are going to transform how you approach this. Okay, let's dive right into it. So pose this question to yourself for a moment. Why is the index register the absolute graveyard for so many top-tier grades? Examiners consistently report year after year that the index register, or IX, is universally misunderstood by students. But why? Well, it really comes down to the heavy reliance on multi-step calculations and the absolute undeniable necessity of method marks. You see, the index register is used for indexed addressing. This isn't just storing a single value. Indexed addressing means you are taking a base address from the instruction and you are adding an offset value, which is currently sitting in the index register, to find the actual contiguous memory location you need to access. It's a journey. You start here, you add this, you end up there. Students struggle with this because this isn't just about defining a term. You can't just say, the index register holds an index. That gets you nothing. It requires a sequence of flawless, logical, mathematical steps. If you rush like our friend Sam, you drop the calculation steps. You might get the final hex value right, but you lose 3 marks getting there. If you just define the term, like Alex, you drop the application steps entirely. You showed the examiner you read the book, but you didn't show them you can actually solve a computer science problem. We are going to completely fix that today, step by step. Here is our clear roadmap for getting inside the examiner's head and systematically building a top-tier exam strategy. We have 4 parts. 1. Core principles. 2. Top examiner warnings. 3. The procedural framework. And 4. Critical analysis. Let's kick things off with Section 1, Core Principles. We need to look at the cognitive domains and foundational theory that Cambridge examiners are actually testing.
All right, so the absolutely crucial point here is understanding these 3 pillars: knowledge and understanding, application, and analysis. The Cambridge examiners have explicitly stated in the 9618 syllabus that top-performing candidates, the ones getting the A stars, exhibit a connected, conceptual understanding across these 3 specific cognitive domains. You have to seamlessly apply them to completely unfamiliar contexts. Now, how do we actually structure this on paper? Top students use what we call the PEAL framework. That stands for point, evidence, explanation, link. Think of it as your structural safety net when you decode a command word like evaluate or analyze regarding the index register. You don't just write a sentence, you build an argument. First, you make your point about the offset. Then you provide evidence extracted directly from the binary data given in the question. Next, you explain exactly how the arithmetic logic unit, the ALU, processes this addition. And finally, you link it all back to the specific context of the question. Why did Alex fail? Alex failed because Alex only gave the point and maybe a little evidence without any explanation or link. Alex just listed facts. Before we continue into the next crucial section about exactly what the examiners are warning against, I have a quick reminder. Subscribe to our YouTube channel, Ace the Exams, @AceTheExams IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. It's the best way to make sure you never miss out on these grade-saving strategies.
Moving right along to Section 2, Top Examiner Warnings, we are shifting to the most urgent part of this explainer by revealing direct warnings extracted right from principal examiner reports. I want you to read that quote on the screen and really, truly let it sink in. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. This brilliantly illustrates the method mark strategy. Listen, in computer science, specifically with the IX register, where you might be taking a decimary number, converting it to binary or hex, adding an offset, checking for overflow, and finding a new effective memory location, showing your process is an absolute non-negotiable. It is the law. If Sam, our rusher, had just written down the binary addition step on the paper, literally just jotting down the 8-bit or 16-bit addition, even if he somehow miscalculated the final bit and got the wrong end number, the examiner would be forced to award a method mark. Those single solitary method marks are literally the difference between a B and an A or an A and an A star. You have to show the examiner your brain working on the page. Now, the examiners didn't stop there. They highlighted 3 specific repeating errors that destroy students' grades every single year. 1, forgetting to check overflow and edge cases. 2, forgetting to check boundary conditions. And 3, providing answers not specific to the given context. Let's break that down. If you are calculating an address using the index register and your base plus your offset results in a number that exceeds the physical memory bounds of the system described, that's an overflow or a boundary condition. You must explicitly state that on your paper. If you just write down a non-existent memory address, you fail the question. And regarding context, you cannot just give a generic textbook answer. It must relate to the specific robotic arm or temperature sensor or memory array described in the prompt. I highly suggest creating a custom mnemonic to lock this in your brain right now. Let's use OBC, Overflow Boundaries Context. Say it with me, OBC. Whenever you see a question about the index register, I want you to physically write OBC in the margin of your exam paper. Imagine we are looking at Alex and Sam's answers again. By applying the OBC check and our Peel framework, we can literally watch those red pen marks transform into green check marks on the screen. We take Alex's generic rambling fact dump and shape it into a tight, specific, context-driven explanation. We take Sam's rushed final number and expand it out to show the step-by-step binary translation. This transformation is what we call the computer science success blueprint. Section 3, the procedural framework. Let's introduce the standardized sequence required to systematically process index register problems without dropping those easy points. But actually, stop scrolling for just a second. Subscribe to our YouTube channel, AC Exams, at @ACExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @ACExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's look at this framework. Here is the exact 5-step methodology that examiners desperately want to see when you tackle complex past paper problems. Step 1, identify key elements. Look at the prompt. What is the base address? What value is currently sitting in the IX register? Write them down. Step 2, apply relevant principles. Are we definitely doing indexed addressing here? Confirm the instruction set. Step 3, execute analysis with clear working. This right here is where you secure those vital method marks. Write down the binary addition. Show the math. Step 4, verify results. Bring in our OBC mnemonic. Check for overflow. Check the memory boundaries. Step 5, present in appropriate format. Ensure your final answer directly answers the command word. If they ask for hexadecimal, do not leave it in binary. Rigorous data interpretation skills are absolutely critical here. You must be able to extract from binary representations, perform calculations, and draw evidence-based conclusions. Let's do a quick mental workshop. Challenge number 1, the data scan. I'm putting a 60-second timer on the clock in our minds. Imagine a complex data table on your screen showing contiguous memory addresses from 0100 to 011F, alongside an accumulator and the IX register. Look at the base address provided in the assembly instruction. Let's say it's LDX0100. Now look over at the IX register. It's holding the binary value 00000105. Your brain should immediately, within seconds, extract the chord trend. The base is 0100, the offset in denary is 5, so the effective address we are looking for is 0105. If you systematically extracted that binary, performed the offset calculation in your head, and located the data at address 0105, you just successfully executed the framework. You beat the clock. Now, beyond just trace tables, the practical application of the index register requires this specific sequence to fully develop and demonstrate your programming skills. Design algorithms, implement solutions, test thoroughly, and evaluate performance. Let's move to our second interactive challenge, find the flaw. I am going to read a sample paragraph written by a student. Listen very closely and try to spot the exact sentence that is going to lose them marks. You have about 30 seconds to figure this out. Here we go. To loop through the 1D array, I will use a for loop. I will increment the index register by 1 each time. This changes the base address, so the program reads the next item. The loop ends when it reaches 10. Did you catch it? Let's reveal the examiner commentary. The fatal flaw is the sentence, "This changes the base address." Listen to me carefully. The index register does not change the base address. The base address remains perfectly constant. It is hard-coded in the instruction. The IX register holds an offset that is added to that constant base address to calculate a new effective address. That single terminology error, confusing the base address with the effective address, will instantly drop you down a mark band because it shows a fundamental lack of understanding. Let's shift gears to Section 4, Critical Analysis. This is the final stage. This is where we learn how to evaluate algorithms and solve problems with the critical, unforgiving eye of a senior examiner. All right, challenge 3, speed writing. Imagine you have a 30-second timer to draft a perfect Peel paragraph comparing indexed addressing with immediate addressing. True comparative analysis requires identifying both similarities and differences. You can't just list facts about one and then list facts about the other. You must utilize comparative connectives, words like whereas, conversely, similarly, or in contrast, and you must support everything with hard evidence. For instance, your paragraph should sound something like this. Both immediate and indexed addressing are modes used to fetch data for the accumulator. However, whereas immediate addressing uses the operand itself as the actual data, resulting in much faster execution times, indexed addressing uses the operand as a base address and adds the IX register to it. This allows for highly efficient array traversal, but requires an additional calculation step by the ALU. That right there, that is a masterclass in comparative analysis. It hits the points, provides evidence, explains the mechanics, and links it to performance. When you are asked to evaluate the overall quality and efficiency of an algorithm that utilizes the index register, you must identify these 4 specific elements: time complexity, space complexity, edge cases, and the effect on performance. You need to ask yourself the hard questions. How does looping through a massive array using the IX register impact the execution speed compared to using direct addressing? What happens at the edge case where the array is completely full? Does the IX register value overflow and exceed the allocated memory space? Does it crash into memory reserved for another program? By explicitly mentioning these 4 elements, time, space, edge cases, and performance, in your long-form exam responses, you signal to the examiner that you are thinking like a true computer scientist, not just a student who memorized a textbook. You are showing them the analysis domain, which is exactly what the 9618 syllabus demands for top marks. This slide brings everything we've talked about together. This is the ultimate deconstruct, solve, evaluate loop for problem solving. Consider this your cheat sheet recap, the definitive system that will secure those crucial method marks. Identify given information, break the problem into logical steps, solve systematically showing all your work, check for reasonableness using our OBC mnemonic, and make justified recommendations based on time and space complexity. To execute this perfectly, you just need to follow our 3 golden rules. Rule 1, command word decoding. Know exactly what analyze versus describe requires. Rule 2, Peel framework application. Always use point, evidence, explanation link. Rule 3, the time management matrix. Don't rush like Sam and drop your method marks, and don't waste time info dumping useless facts like Alex. Allocate your time based strictly on the marks available for that question. As you apply these 3 rules, you can practically see your mark potential progress bar shooting all the way up to 100%. So I leave you with this final provocative challenge. How will you apply this method mark strategy to your next past paper? The knowledge is entirely in your hands now. Look, students who actually implement these specific computer science strategies see an average improvement of 2 whole grade boundaries. But that only happens if they practice consistently with our weekly explainers. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Before you go, drop a comment below with your target grade for computer science and the biggest challenge you're currently facing with registers or assembly language. Our team responds to every single comment. Like and share this with your study partner. Ace the Exams. Your Cambridge success starts here. Take these frameworks, decode those command words, and transform those red marks into green check marks. I'll see you next time.